Ah, você tem... Ah, daí... Uhum. Oh, perfeito. Boa pergunta. O que eu posso falar mais baixo? O bom é que o som tá perfeito, porque minha garganta é inflamada. Então, todo mundo vai ouvir o que eu tô falando. Eu achei que não ia dar tanta dor de cabeça pegando deixando minha mochila na minha sala lá. Mas aí, só vou mandar pro Lucas, tá tudo certo. Então a culpa é minha. Peço desculpas. Hoje em dia é daqueles, né? Tranquilo. Não, tô tranquilo. Depois que você falou que. É pra esse tipo de coisa que se reserva uma hora a mais na sala, né? Tá tudo certo. Aham. Eu esqueço que se eu dou para as pessoas, daí reverbera, né? Mas, Lucas, eu acho que é culpa minha mesmo, porque é a primeira vez que eu não trago meu pendrive com PDF. Eu sempre faço isso. Aham. Teste quanto tá. Você me Ok, então vou ficar aqui desse lado, então. Eu sou o microfone.
Welcome. Thiago. Raszeja, right?
Kind of.
About
So thank you very much, Lucas. Thank you very much for the organizers of this seminar. It's a pleasure to be here. I was going to apologize because at the moment I have a sore throat, but thanks to the audiovisual team, everything will be fine. I don't have to force my voice. So this work, it's something we have been developed during Ivan Masters. Basically, there's after we started the study of a generalized thermodynamic formalism on this generalized space. Many questions that are nature from both sides of dynamical systems, or even or sister algebras, and in this case, it's spectral theory arises because these kind of questions started in the standard Markov shift case as well. So this talk, it's divided basically 3 parts. I introduce the generalized Markov shift space coming from the standard one. The second part, I will talk about what is weighted endomorphism or weighted shift operator. And the last one is the application for this, this space, this generalized space. Okay, so first let's talk about Markov shift spaces very briefly. So in general, we start with a countable alphabet and a matrix of 0 and 1s, which describes the transition between these states in this alphabet. And the Markov shift space is the space of infinite sequences, such that 2 consecutive coordinates of the sequence, they are allowed by this matrix. And here we use the subspace topology of the product topology. And also we have a dynamics here, which is the shift map. Basically, it's a local homeomorphism, such that we just erase the first entry. And some topological aspects here, I tell you it's a word, sometimes element of a free group, I will describe it later, and sometimes it will be a set of symbols, finite set of symbols. And this topology also is generated by the cylinder sets, basically the sequences that start with a fixed word, finite word. And we say that admissible words are those whose the cylinder is non-empty. Okay, so this space actually is a Polish space. We can find explicitly a metric for this, and also it's zero-dimensional. That means it has a basis for the topology of a co-open set. Okay. Well, some examples that we use, it's the full shift. This doesn't depend on the alphabet. Basically, every symbol can connect to every symbol. And the renew shift, were basically described by this graph. I mean, there's an arrow if the matrix allows the transition. For example, if A1 to the symbol 2, it's allowed because this is 1. See? And this is the matrix. And part of the standard hypothesis here is the transitivity. In other words, we say that the shift is transitive if and only if its matrix is irreducible. And basically, in terms of shift, we have, if you have 2 symbols, we can connect through an admissible word such that the whole word starting from A, passing through W, and going to B is also admissible. And as some topological facts about this, the first one actually doesn't need transitivity, but the rest needs. If the alphabet's finite, so the shift is compact, and if it's infinite countable, and the matrix is row finite, that means each row has a finite number of 1s, it's locally compact. But in general, it's not compact at all. And the remaining case, it's when the space is not locally compact. And this space, when you approach by the finite symbol way, you connect this by what we call it a Cuntz-Krieger algebras. And in this case, I will not show there's a universal sister algebra way to present this. Actually, I will avoid this and just use a representation which is faithful, so it's easier to make your accounting. So it's more under control, we say. Okay, so we start with a Hilbert space, in general not separable. And this L2 has a canonical basis. And we have these 2 partial isometries. So sorry, we have this partial isometry and it's adjoint. So when you apply for each element of the basis, you can define this in the whole space. And this basically does the following. If I can connect I, so it connects this. If it's not, it's 0. And consequently, its adjoint checks if it starts with I, and then we remove this I if this assertion is true. And from these partial isometries, we can construct some projections here. This one basically checks if the X belongs or not to the cylinder I, and QS verifies if the X it belongs to this, the shift. When they take the cylinder, they just shift it. So we verify if this holds. Case shift of I. Okay. So in general, including the case of the finite alphabet, what we have, let's see. So I'm talking about Cuntz-Krieger algebras. We can construct this sister algebra. In our case, it will be unital. I will talk later. I will say some conditions that it's insured. In general, it's not. And the original construction, we start with an algebra that contains this algebra, and its codimension is less or equal to 1. That means it's the canonical unitization when it's not unital. So let me explain what these generators do. Okay, so this shows in the blackboard. It's okay. Okay. So let's say we have this element here, and we evaluate on some delta X, for example. Okay. So let's draw X like this. So the first entry, when you write this, let's say that gamma is a word like gamma O, gamma 1, blah, blah, blah. Gamma length of gamma minus 1. That's the gamma word. So this is basically the juxtaposition in the order of these operators appear. Okay, so what this, and if you take the involution, you just change the order and apply it to each element as an evolution does. And this first operator, he sees, he gonna look, this I, look if this beginning is a beta. If it's not, it's 0. If it's yes, then this operator cuts it. After that, we have, suppose that it's non-zero. So what we have here is shifted the length of beta times X. So this first letter is X beta. So now what these quill operators do, it's basically we check if it's possible to, if these elements, they are contained in here for each one. So there's two options. If it finds something that's not connected here, it'd be 0. Otherwise, it remains unchanged. And the last part is this is the product I in F QI. And for the last, this one checks if it's possible to add gamma here. So in the end, we have, if it's non-zero, so this should be gamma sigma length of beta times on X. And so basically we we're putting some glue here. Okay, this is basically what these operators do. And if we look define as this way when the first word and the last word are equal, this is you construct a set of pairwise commuting projections. So this is a commutative sister algebra generated by projections. And it's one important thing, this is unital if and only if this is unital. So since we're talking about, okay, so before I continue with this, I use two types of ways of representing this DA. This is the main, this is the main object of this talk, we say, okay? In the sister algebra way. So this is a free group. If you have the free group generated by the alphabet, we also can define another set of generators that we can also construct this algebra. So basically you take a symbol, this is a natural number, you take to this TS, S-1, you take to the TS star, and if G is a reduced word in F, you just do the juxtaposition, and the identity is 1. So see, it's not in the algebra. This is a bigger algebra that contains OA. Okay. Okay. And it's so this sister algebra actually is isometrically isomorphic to the sister algebra generated by this set of projections. So we have two sets of projections. You can start use one type, another type. You can construct the same algebra. Why we do this? Because sometimes it's easier to deal with this. Sometimes it's easier to deal with this. Okay? But in the end, they generated the same thing. And they are related to each other like this. So basically, you use proof of this identity to show that actually this isomorphism holds. Okay? Okay, so we have a lot of algebraic stuff here, but now let's go with a little bit of analysis. And so if you have a commutative sister algebra, you can talk about the spectrum of this algebra, which is the non-zero star homomorphism from the algebra to the complex numbers. And the generalized Markov shifts are the spectrum of this algebra. And here the topology is the weak star topology. Okay? So basically, in terms of story, for the Cuntz-Krieger algebras, it's already known that this it's isometrically isomorphic to the continuous functions on sigma A. But in this case, for finite alphabet, this is compact. So you can apply directly the Gelfand theorem for commutative sister algebras, okay? But you see, so many times, I mean, even in the very simple shifts, like the renew shift, this is not even locally compact. If it would be, you could use C0, it would be okay. So XA is the natural candidate when you deal with infinite alphabet in the very general way that you can make this construction. Okay? Well, and also I have a disclaimer to make. Usually, when I give talks about this space, I start the approach of the geometric way of describing this. So usually you have this is space O1 power F. F is the free group generated by the alphabet. But lack of time, I won't be able to do this. I will do it in the analytic way. But if you're interested to see in a more geometric way of approaching this set, I recommend to watch the Rui Exel's talk at ICM. So if you type this on YouTube, 2018. So if he presents the geometrical way. So because you have a group, a free group, so you have a KD3, so you can see these are configurations on the KD3. I don't have time for that because it's a long road. I thought it's a beautiful road, but so let's do the things in the analytical way at this time. So, okay. So how this is important. Somehow this should be a generalization for the idea of Cuntz-Krieger algebra. So it's natural that this could happen. So how we introduce this? Basically by this canonical map, when you take an element of the shift and you obtain this character of the algebra. So it basically is the evaluation on the delta x. Remember that the elements of dA are diagonal operators. So it's kind of easy to make evaluation for this in this way. And just a little bit of story about this. This topic of the Cuntz-Krieger algebra and its generalizations dates since '63. So the first Dixmuir, he proved the existence of a simple infinite star algebra, and the first concrete example was constructed by Kuntz, Joachim Kuntz, and in this case, basically, is the full shift. The matrix is completely filled with ones. Every entry is one. And by curiosity, also this includes the infinite alphabet, but this is a very particular case. Later, 3 years later, Cuntz-Krieger, they connected this notion with Markov shift space, in particular the compact Markov shift space. For example, this identity is part of the consequences. So this algebra, in other words, it codifies the Markov shift in terms of operators. This is the spirit of this. Later in '97, Kumjan, Pesk, Reburn, and Renault, by using theory of group or star algebras, they went even further for the row finite case. And finally, in '99, Exel and Exel-Laca, they removed this condition and made it in a very general way. Later, Renault did the groupoid approach that it was started in this work. And so, but since then, there was no thermodynamic formalism constructed for this space. So this is basically the theme of my thesis and 2 papers with Rui Exel, Rodrigo Bissacco, Rodrigo Frauzino, and me. It was about to start in this direction of the thermodynamic formalism, which was already started a long time ago for the sigma A case. And for the most recent thing, I mean, okay, just let explain some stuff. There's some measures of interest in the thermodynamic formalism, like the Bruching, Lanford-Hoel measures, the conformal measures, chemistry states for the quantum side of the theory, and the eigenmeasures. These measures, they have the thermodynamical meaning in this theory, and also dynamical meaning in this theory. And we discover new measures here. We discover new phase transition phenomena, and we construct a notion of pressure that plays with all the sides of the space. Because the complement here for the infinite alphabet in general is not empty, and it's dense in the whole space as well. And lately, I had the pleasure to meet Yoshida in the conference we have here. at IME, and he presented about this new work of them, Ichimoto, Nakano, Toyokawa, and Yoshida, about the non-commutative entropy for this space. Actually, the sister algebra, I wrote it wrong here. It's OA. Okay, this is for the Exel-Laca. So, okay, going back to this space. So the usual way how this works is we include this in this space, and actually in the end we can alternatively take this closure about the types of about this by using this inclusion. So this goes to a space of characters, and then you take the closure, so it's dense. Sometimes you have to remove, but in compact case, you don't have it. Remember that I wrote two types of projections. What happens when you look at this phi O, it's defined by like this. It's 1 if G equals to E and 0 otherwise. So actually, you see this as a character in a bigger space. But when you restrict this to the algebra, this must be excluded. This never happens for a compact case. And one sufficient condition for that is when A has a full row of ones. For example, renewal shift, for example, full shift. And there's many others, like a family of shifts you can do this. Okay. So now this is pretty much some relations we obtain about this inclusion. So first, this is a topological embedding, and it preserves the Borel sets. And second, if sigma A is locally compact, these two sets coincide, which is good because it recovers, in fact, the previous theory for the row finite case. And finally, this I told before, if it's non-empty, so it's also dense in the whole space. Okay, so I thought a lot about sigma A, but what should be the new elements of this space? Okay, it's you take since this is actually XA is a metric space, so you take sequence, and since it's compact, every sequence should have a convergent subsequence. In particular, even sequences that explode the symbols. So what I mean with this is, for example, the elements, the new elements, they are characterized by a pair stem root. How this appears? You must take, for example, suppose if it's empty, it's the same way. I will talk about when this is not empty, okay? But in general, is like this. You have a sequence in sigma A, already considered inclusion, and this there is a symbol, an n, and some point that the beginning coincides with this. So for n big enough, we have omega. Let's see, dn, this is a symbol here, and what happens next, okay? And in order to be outside sigma A, this symbol basically explodes. So the new elements are taken by sequences that explode because you know this space is compact. So this should be a convergent subsequence. But in fact, this converged like this. So this, in the end, it's could be like seeing like this is evaporating, so everything here is appearing, and this air actually is connected to these elements. So suppose this converge. So you already took the subsequence. Look to the matrix. So you have D1, D2, blah, 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 Dn, and keep going. So these are the columns of A, and you can see these as elements of O1 power n and product topology. So in order to this converge to this element, when you take this sequence, it should converge to a matrix. And for the compact case, this never happens to be 0. And this is read like this way. So this set R is a subset of the alphabet. In such a way, when you take this limit, K belongs to R if and only if dk is 1. Okay? And consequently, we can also define the shift map for these elements. So here, FA is finite when this is a finite word but not 0, not empty. This is the case. These are the elements who are empty, and these are the corresponding to infinite sequences. Okay. So when you take the shift here, basically you're shifting here, and when you shift this guy, you shift here. But see, there's a question that there was before when we started the thermodynamic formulas. Actually, this dynamics is not defined here. Why? Even the potentials when you do the thermodynamic formalism. But in this case, we are interested on ways that this could have types of matrices that this could have continuous extension. Okay. For example, the renewal shift. The only possible limit here is this matrix. So that means let's see this example. Should be more elucidative. So this basically says that. Oh yes, there's one more thing. This word should end because this diverges. This should end in an infinite emitter, and all the elements here are infinite emitters. Because when you take the process of the limit, these guys should appear in infinite amount of times. From some point, this always happens. And when you do this for the renewal shift, we have these extra elements are like this. See? Only element 1. And also omega 1, where omega ends in 1. So these are the new elements. How you evaluate them? Take the sequence, apply for the take any operator, e.g., apply here. And this limit should be, for example, if this converges to omega, there's only one option, so this should converge to omega 1 e.g., for example. Okay? So now the second part, it's about the weighted shift operators and weighted endomorphisms. And it's the idea of let's start with some easy conditions to define this. So you have a Banach space, a Banach subalgebra, and you have two bounded operators on the space that satisfies this. In abstracted way, a weight shift operator, it's this type of operator. But there's some questions. I mean, I defined a shift map here before. So what's the matter? What is this named shift operator, and why weighted? Okay, weighted. It's basically because we have this element here. So somehow it gives a weight. But why shift operators? And it's possible to see this in another areas of mathematics, and the answer is here is yes. So this is kind of answered. We should see this case and this case, but I started with the question 2. Sometimes life is not time ordered. Okay. Let's take, for example, in measurable dynamics, you have a measurable space when mu is a sigma finite measure. So you have a dynamics, invertible dynamics, whose inverse is also measurable. And we define it's such that these measures are equivalent in the sense of absolutely continuous. So I can talk about Hadonic-Odin derivatives here. Okay, then you define this for LP, and you define these 2 operators, and these operators, they satisfy more than they satisfy these that I stated before, but also if you make this product, it belongs to the commutant of an algebra A. Who is A? It's the algebra of the multiplication by an element of LME infinite. Okay? In this case, this is a weighted shift operator. Okay. Another case, complex analysis. So we take this Cauchy-Value, principal-value integral here, and we can define this operator. And in this case, it's in the unit circle, and you give it from L2 to L2. And in this case, you can choose A as being the algebra generated by the multiplication operators, as in the last case, but in this case, continuous, and the compact operators. In this case, actually, the Poincare-Bertin equality is exactly this identity. So this is already known from complex calculus, and this is a compact operator. So in other words, actually, in this case, we have T equals S, and this is AS should be the weighted shift operator. So we have examples in different topics. And so now it's when this start to connect to what do we want. Many of the references here are the paper of Bartosz Kwaśniewski and Andrei Lebedev, and this most of the results I present here, they are a little bit more general, but I interested to restrict this to the C-star algebra case. Okay, so if you have a unitary commutative Banach algebra, and so you can talk about the spectrum of this algebra, and you have endomorphism. So in this case, there's a unique continuous map that defines a Klompen subset of the spectrum. That this is such that it satisfies this. This hat is the Gelfand transformation. I mean, this is you apply the Gelfand transformation here. So I need the eraser here. Okay. What we have in this case? So alpha A x, this means that x alpha A. Remember, this is element of the algebra, and this is in the spectrum of the algebra. So this is actually, when you apply all this is a complex number. Okay? So this is a function. Okay. And in this case, when the endomorphism is unital, it's equivalent to delta B the whole space. So you can define this in the whole space. And in this case, when we restrict this to the sister algebra, actually this connection is 1-to-1. So if you start with the dynamics, you find endomorphism. If you start with endomorphism, you find the dynamics. And this map is called the partial map dual to alpha. Okay? Okay. But now, we are talking about weighted endomorphism. So from some point, I have to move from weighted shift operators to weighted endomorphism. Sometimes I have to introduce this thing. But in order to construct this, basically I put some conditions, extra conditions, to the weighted operators, and then I can construct the endomorphism. So this is a weighted endomorphism. In other words, you take two mutually adjoint partial isometries such that they are contractions, and if they satisfy that weighted shift operator condition that stated before, then this is an endomorphism. So this guy is the weighted endomorphism, and these are the weighted shift operators. Okay. So the main thing about the work is to find an explicit formula for the spectrum of these operators. So this is the my objective here today. Okay. So now I'm gonna explain you why this is called shift operator. Because when we start from sister algebra, actually it's a little bit more general than this, but for us, sister algebra always. You have this star endomorphism, so you can find a Banach space of sequences of with each xn belongs to this set. And when you can find a unitary isometric homomorphism and mutually adjoint partial isometries that works exactly like this. So basically, you find a way to represent this such that T and S acts like a shift. So you cut the first entry, and this is like the shift to the other side. So this is why we call this shift operators. Okay? So this is so now all the questions I stated before, they're all answered. Okay? It's funny because nobody asked it, but I just okay. So in this paper, the same paper of Kwaśniewski and Lebedev, there's this result about the spectral radius of this shift. So basically, it's equals to this. I mean, when I write this for me means that I have to put something here and then multiply by A. And this spectral radius is equals to this one, and it's basically this limit. And in particular, this is satisfied for every k natural number. So every interaction you do with this on this endomorphism. Okay. Now, so there's an abstract way to construct, make the ergodic properties approach for this in a very abstract way. But in the end, all these sets, they are for our approach, just to let you aware, although this construct can be a little bit more complex than the usual, but in the end, every one of these guys, it's XA, okay? So don't worry. In our particular case, this is the whole space. But in a general way, when you have a compact Hausdorff space, you have this partial dynamic system. I mean, the phi is defined in the subset here we, I mean, partial means that it's not necessarily defining the whole space. That's the point. So we can define these sets. Just take pre-images in the inductively way, and when you take this, for example, take delta 0, so delta 1 pre-image of delta 0, and then you keep doing this, and in the other way you take the range, okay? Instead of pre-image, you take the image. So the essential domain of a partial map is this set, and in this case, the map is ever defined and surjective, and the invariant and ergodic measures, they live in this set. But I have a problem. In our case, this should be XA. So is there a way to refine this, make this easier to compute? Or there's a subset that you can, here inside, that you cannot deal with the whole XA? Yes, you're going to discover this. I'm going to tell you. And the last theorem of them I'm going to explain is when you have an endomorphism of unitary commutative sister algebra, you have this partial system dual, like the connected, that way I told you. So the spectral radius here is the maximum over the measures that are invariant in the space. It's equivalent to say they are the maximum over this maximum value of this on the ergodic measures in the space. And more than that, something that is not usual. This is a continuous map. I mean, it's not necessarily general and true that a spectrum of operator could be continuous when you index this by some map. This is not true in general. So this is a very special property. Okay. So now the final part. Let's apply this to generalized Markov shifts. And what we did in this work is a couple of results that we are able to apply this to the theory of Kwaśniewski and Lebedev. So first, we found, for the case of the shift map, we found explicitly what should be the endomorphism associated to this. So you have this dual map. Remember, sister algebras, uniquely determined. But, I mean, you can extend this from the generators I told before. Remember, TG, TG, TG star. So this, you are possible to extend this to the whole algebra in the way that this should be a star endomorphism if there exists a continuous extension of the shift to the whole space. So this is explicitly determined. And in particular, this is always unital. So there's no confusion here. I mean, this respects the theorem of the dual map when it's unital, and a couple of properties I told before. It's the algebra is unital, the endomorphism is unital. So this is sister algebra, so it's one-to-one. But this is actually don't need to state that alpha is unital because it's a consequence. Okay. So okay, and question. Okay, we have this condition about the extension to be able to proceed with the theory. But what class of examples we have this? So the class of examples, it's something we discovered. And we name it periodic renewal class of shift space of matrices. So let me explain. Oh, it's basically like this. There's some conditions. Actually, just a disclaimer. In the paper of the Nakano, Yoshida, and about that paper about the commutative, non-commutative entropy, they have examples that could be extended, but it's specific to one empty word. So here you don't have this limitation. You can, for example, the pair-renewal shift, which should be, for example, basically spoiling the renewal shift with extra edges. So remember, this is the renewal shift. So this happens. So and in 2 goes to every even symbol. So you can add this more. This has 2 types of empty words. You have this and this, for example. They are different. They are in the space. And sometimes this is the good part. And this is the dynamics that interacting each other. Okay, so let's describe what should be this periodic renewal class. First, XA compact. That's equivalent to say, A is unital, DA is unital, and there's now a better and more general condition. The set, I mean, if you take the sequence of columns of A, you take all the limit points you can do here. If the 0, 1, the 0 vector is not a limit point, then it's compact. So this is equivalent. It's completely general. And so this is the first condition. The second condition is that there's a finite number of infinite meters. And we call it the last one like NE. And also, if you see this summation, this is over I. So it's mandatory that the matrix should be column finite. I mean, every column there's a finite number of ones. So a column finite. And when you have this number here, you should be able to construct up to a transitory phase here. You should have a matrix that it's say M and E times M, which all of these columns are different. So I mean, it could sound weird, but we'll see counter examples, so it should be more clear. Okay, and the rest you complete as you are in the renewal shift. Okay, so basically the renewal part about the coming back to the first symbol. And one example is the symbol I told before. This is the pair renewal shift. Only 2 empty word configurations. I mean, empty word elements of the generalized shift. And in this case, there's a continuous extension that maps one empty word to another one, and vice versa. So basically, it's like this. Shift, shift. This is already beyond well-known, some examples that are already known. So this is the part of the news. Because, I mean, the explanation for this, it's because if you, up to, you say, if you have convergent sequences here to the outside the sigma A, after some symbol, this should be only on these forms. I mean, there exists an n big enough that should be the sequence should be reading like this. So this is odd, this is even, and this is odd. So if you take this element going to infinite, And this is actually where the column finite condition also works. Because for column finite, if you take a sequence, when the symbol explodes, the next one should explode, the next one should explode, and etc., etc., etc. And these two sequences, for example, this goes to this element, this goes to this element, and when you shift, you just change it. This is odd. Now shifted becomes even because of this type. So this is why this is well defined. I mean, any sequence that converges to these guys, the only remaining part of the space should extend the dynamics. You have a continuous. You have continuity. Okay? If you make this choice. Okay, another example, more general. Instead of taking instead of taking two empty word elements, you have n empty word elements. So basically, you have this matrix like this. You have 1, 1, 1, 1, 1, 1, and until you reach 2n. So basically, this triangle repeats, repeats, repeats. All the columns are different. And the empty words here are in this form. So if you take periodically, this guy 2n, 3n, go on. You can do this for each element here. So these are the empty words, and when you shift the type of the sequences you take, again you have this type of extension. So see, it's decaying. So you are here. So you shift, 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 reach the E1, shift again. So it's a cycle. Okay? And so now let's comment about some counterexamples about this. I mean, let's break some conditions. For example, let's suppose that the columns are not equal. Okay? What happens? This is an example. So the matrix here, you can look like these 6 elements. So this repeats, you see? So you can base it on a sequence of columns taking 4, 7, and go, 10, and you go. So like something like this. And you can take another sequence, like 5. Let me just check. No, it's 1 should be 2. Go to 6. Yes, 5, then 8, then 11. Keep going. Okay. So in this case, these two sequences converge to the same element. Okay? Because both of the columns, they go to the 1, 1, rest 0, okay? But when you shift, one of them is pushed to the another, to this kind of column, and the another sequence is pushed to the previous column. So you have two sequences that converge to the same point, but when you shift it, each sequence goes to a different point. In particular, okay, so there's a result that says when the matrix is column finite, we proved this, that if it's column finite and it's continuously extended, empty words are mapped on empty words. So this is not, this is actually, it's planned because there's a hypothesis. But you see, the only way you have for extension, you make two different points, so it's not possible to have a continuous extension. Okay? And another counterexample is when you take infinite quantity of infinite emitters. It's called the prime renewal shift. I mean, it's basically, again, this types of shifts, basically, I spoil the renewal shift in some way. I add extra edges. And in this case, we take prime numbers, and it's the extra edges is basically prime number going to these powers. And in this case, you have a countably infinite quantity of empty words part of the shift space. Okay? And again, we can construct two sequences here that they go to the same point, and when you shift it, they go to different points. Again, not possible again. So this is something you found. This you must have at least for this class. You try to break any of these conditions for this class, you won't be able to extend continuously. I mean, it's like sharp. If you remove, you find a counterexample. It's unavoidable. Okay. And finally, there's because we have this explicit construction for the endomorphism, we can write an explicit formula for the spectral radius of the weighted shift operator. In other words, the weighted endomorphism. So, in other, what I mean with this, remember A alpha. Okay, this is we have an explicit formula for this case. So, in this case, so renew shift is pretty easy. There's only one empty word, so this goes to itself. And star endomorphism preserves unity because this is the result of equivalence. In this case, the space is a whole space, as I told before. The spectral radius of alpha is 1. And what you do is we check this for every element of a span of the A. And because the continuity, the results of Kwaśniewski and Lebedev, you can extend this to the whole algebra. So this is the trick. So if you know for these elements, you know for everything. And so let's take, for example, element of the span. Now, remember, I changed in again the notation because easier to make accounting. Okay? So now, sorry. Oopsie. Okay. Thank you. Now, E gamma F is T gamma product on F, I in F, Q I of each element of F, T gamma star. Okay? That's the cutting and gluing operation I presented before. Okay? In this case, here you can write in this way. So this is sometimes this could be 0, could be not, but I treat on each case. Okay, and so these are all the possibilities we have. So if this Fk is empty, so because of if you remember the definition of the algebra, this is mandatory, or this is no empty, or this is no empty word. You must choose one. But if it is in these forms, so you have two options again. So gamma key can be not the empty word. So you have to impose this condition on the nk, or if this is 1, we must impose this is different of A. So all the rest would be 0. So this is why. These are the elements that are candidates that are non-zero when you evaluate when you try to evaluate the spectral radius. So this is why you have to choose. So because these elements could be 0, basically like this. Okay. So in this case, we have these formulas. In general, now this is an important thing. Remember that I told you that this is should be actually x, but this is the interesting. If you have an invariant measure, so you have an invariant measure with respect to sigma on xa, okay? So if, for example, it gives mass to Fa, okay, thank you. Last slide. If you give mass to this these elements, since in most of these cases they are countable, so let's evaluate this. For example, let's take something like this. If it's invariant, this should be true, okay? But for example, in these classes of cases, especially in the renew shift, when you take the pre-image, we recover this plus, let's say, F1A. What is F1A? The elements such that this has only one letter, okay? But this is a closed set, and this is also a closed set. So these are Borel sets. It's the union of these joint sets. I can separate. It's a measure. So we have this. See? So see, this is, if you give mass to this, it's a contradiction, because again this becomes 0 again. See? So this is why you can simplify this. Just the invariant measures are the ones living here and here, and consequently the ergodic measures as well. And so the formula is basically like this. You construct this product of values. Here, omega A, oh, I have a laser. The omega A is this set. For each of these combinations, you have a set, a number NA, and a set that you can write down this product. In particular, for lambda 0 equals 0, you can find a subshift with on a finite alphabet, and you can make this calculation as well. So you take you can go to this is a result involving the optimization theory, but in general, these lambda x, they are these sets. So if you take sequence here, every sequence, so the elements are 0 or 1, and these elements are determined by this which one you take in the product. And Zx is the intersection of standard cylinders, I mean cylinders in the sigma A, not in the XA. And this tilde means that depending of the element of this finite sequence, it could be the cylinder or its complement. So this is the completely explicit formula. So now it's continuous, so it can extend for every A. Okay? So this is a little bit of the literature. This is the paper about thermodynamic formalism. Papers of Cuntz-Krieger. This is the part of maximizing measures I told you in the ending of this calculation, and this is the thesis, master thesis of Ivan and Exel-Laca, and the main paper of the references of most of the results we're presenting here from Kwaśniewski and Lebedev. Okay, so thank you very much, and So, yes, yes, yes. Yeah, I mean, let's like let's go to the. Oops, maybe it was too fast. Okay, so I mean now we have this construction, right? So basically, one of the things I can tell you, it's this weight because of this result. I mean, this is only for t, see, but you can what you're evaluating is the weighted one, so it's a times this thing. So in a certain way, the spectral radius depends of this a. So this is why it's weighted. So this is why the changes is the because I mean this is it's actually it's a more spectral theory interest question because of the examples I told you. So I believe that Kwaśniewski and Lebedev, when they started to do this, they wanted to extend this already developed to there's some examples of this, some case of this. So they try to see there's something interesting from the point of view of spectral theory. So this is, I don't know if I answered your question or not, but this is also something I was thinking about. Maybe there's more changes beyond this, but in the end it's because when you construct, I mean, you see, you start from a shift space, go to a Banach space, then you have another shift space, but they are not the same. Yeah. Thank you very much. I believe they're not the same. Nossa, tô. Olá e adeus.